In the last video, we started to gain an initial intuitive idea of how to define a force. We will loop around soon in the next couple of videos and give a better definition. But for now, we can take our intuitive definition and we can start to think about how to identify and represent forces. So let's say that you've gone skiing on some reclaimed dump that gets euphemistically called a skiing hill. And so you're grabbing the tow cable to go up the hill, like so. So there's the hill, there's you. It's kind of cold out, so sure you got a hat on, right? And then you're holding on to the tow cable. All right, so how could we go about identifying the forces that are acting on you? Believe it or not, the start of drawing this picture, and let me do a little better job of drawing the snowpack here. Believe it or not, but just drawing this picture here is already a really good start. All you need to do to turn this picture into a force identification diagram is draw a circle around the object you want to analyze, in this case, the skier. Now, this will help you to identify the contact forces that are in the problem, because every time the circle cuts through something, that's a contact force that's going to be exerted on the object. So we can go ahead and label our contact forces. We can start by looking over here, and we can see that the circle is cutting through the rope, and so we recognize that this has to be a tension force. So we'll call that usually T. And since forces are vectors, we'll draw a little arrowhead over it. Okay, does the circle cut through anywhere else? Yeah, it does. It cuts through the snowpack. And it turns out here we'll have two forces. We'll have the normal force we've already discussed in the previous video, and we will also have friction from the snowpack on the skis, which we're holding off on doing more with friction for a bit, but it's still there. And in fact, specifically, it's kinetic friction. So you can put those into our list of contact forces as well. You can put down a N for normal force. And then conventionally, kinetic friction is a small f sub k. Now the only thing that's left is to figure out, are there any long-range forces acting? And yes, the reason the skier has to grab onto the tow rope at all is that they're going up the hill. So that means that gravity must be pulling them down. Now, my preferred notation for the force of gravity is F sub g. As we get into gravity later, you will see that I'm not the biggest fan of calling it W for weight, but I will hold off on that until the appropriate point. But just know that my preferred notation is F sub g. Okay, so with that, we've identified all the forces that are acting on the skier. So this is what's called a force identification diagram. Now, when it comes to actually thinking about how those forces are going to act on something, Just like we were doing with motion diagrams, as long as we're not worried about how our skier might be rotating, we can go ahead and do what's called a free body diagram for our skier. And actually, let me leave the force identification diagram up. So we're going to start a free body diagram. And these are sort of bread and butter for doing force analysis, so they are well worth studying. All right, so as long as we're not worried about rotations, or just like with the motion diagrams, we can go ahead and just represent the object that the forces are acting on with a dot. And then what you do is you attach to the dot, you put the vectors, you put the tails of the vectors on the dot, pointing in the direction that the forces are being exerted. So let's start with our contact forces going down the list. Tension. Okay, so the way tension works, remember, is that the rope is actually a little bit longer than it wants to be. So it's trying to return back to its original shape, and so doing is pulling the skier up the hill. And because it's being, the rope is trying to return back to its original shape, the force is being directed along the rope. And so there we go. So we draw the arrow parallel to the rope and going up the hill. Okay, normal force. Remember, normal is, there's the normal 1 and the normal 2 in the dictionary. This is normal 2, which means perpendicular to the surface. So you ask yourself, what surface? Well, that would be the snowpack. So the snowpack is going like this, which means the force is either going like this or like that. And the other big clue is that the normal force is keeping the skier from crashing through the snow. So it must be that it's pushing up-ish on the skier, trying to keep it from going through. So we'll go ahead and draw in our normal force, like so. All right, next on the list, kinetic friction. Friction will always be parallel to the surface. The only question is it going up or down the surface? And for that, we would have to know some details. Well, here, if you're being towed up the mountain, right, your velocity is going up the mountain. That means that friction is trying to oppose the motion, and it has to be parallel to the surface. So we can put in F sub k. And then that just leaves our long-range forces. Well, at the surface of the Earth, gravity always acts down, and by down, I mean straight down. So there we go. We have drawn a free body diagram for our skier. And then when we get to looking at Newton's laws of motion, we'll find that this is very helpful for figuring out how the skier is going to accelerate, or if the skier is going to accelerate for that matter. So one other thing that I would like to introduce in this video before I go to the next one, so I would like to introduce the concept of net force. So let's say we've got a boat here going up the river or something like that, and there's two tugboats that are pulling on our boat. So we can go ahead and look at the forces due to the ropes. So if we draw a quick free body diagram for that. And yes, I'm aware that gravity is going into the page and there's a buoyant force from the water going out of the page. I'm neglecting that for now. There would be a force due to tension from the cable attached to tugboat number 1, and there would also be a force due to tension from the cable attached to tugboat number 2. So the idea of net force is that if I were to add these two vectors together, so here I'm going to go ahead and use the parallelogram rule. The vector sum of these two is the net force. So just net just means the result of addition. So after you've added up all the forces, in this case doing vector sums, this is what you get. So this net force isn't a different force of nature or anything like that, but it'll turn out that that this boat will behave the same way under the influence of these two cables as if it were attached to one cable pointing in this direction, pulling this hard. The motion will be the same. So the reason that we can add up forces like that and get the motion to be the same is an example of what's called superposition. It's what it means is that you can, to figure out how forces are acting on something, you can first pretend that, say, this was the only force in the universe acting on the tugboat. And then you can pretend that this one was the only one. And then you can say the combined influence of the two is the sum of the two. It's one of those things that seems blindingly obvious, but it's not at all obvious to why nature has to work that way. We're just extremely glad that it does. Okay, so with those preliminaries out of the way, in the next video we will go ahead and take a look at Newton's first and second laws of motion. So catch you in the next one.